You place a pot of water on an induction cooktop. Just minutes later, the water is boiling vigorously. But here's what's truly mind-bending. The glass surface beneath it is barely warm to the touch. If you've never seen this before, you might think something fundamentally contradicts everything you know about cooking. Normally, to heat a pot, the cooktop must heat up first, right? That's how we've always done it. But induction cooktops seem to break every rule you've ever learned about heat transfer. The pot heats up almost instantly while the glass remains cool. Many people assume the glass must be made from some miraculous material. Others believe the heat is somehow hidden somewhere, invisible during the cooking process. The truth is far more fascinating than any of those theories. Induction cooking is actually one of the most elegant applications of physics ever to appear in a modern kitchen. Instead of creating heat somewhere else and transferring it to your pot, this technology essentially makes the pot create heat from within itself. It sounds like magic, but everything happening follows strict, unforgiving laws of physics. The secret lies not in fire or glowing heating elements, but in something invisible that surrounds us every single day. This invisible force powers electric motors and generators. But unlike those familiar devices, induction cooktops use this force in an extraordinarily clever and efficient way. To unlock the mystery, we must answer, what exactly is heat? Many people believe heat is something created and then transferred. The physics is more fascinating. Every object is made from atoms, constantly moving billions of times each second. When atoms move faster, they carry more energy. We feel this as rising temperature. Heat isn't an invisible liquid. It reflects kinetic energy inside matter. Every cooktop's basic job: make atoms move faster. Wood stoves burn fuel. Gas and electric stoves use the same principle. Create heat at the source, then transfer it to the pot. This method accompanied humanity for thousands of years, but has one major problem. Significant energy is wasted before reaching food. That's why kitchens become hot, even though most energy should be cooking. Induction cooktops deliver energy exactly where needed from the start. It's like cutting out the middleman and sending energy directly to where heat must appear. This involves electricity and magnetism working together to make your pot create heat from within. Beneath the glass sits a copper coil wound into loops. This generates a powerful, changing magnetic field above the glass. The coil needs electrical current different from household electricity. Home electricity oscillates around 50 Hertz, but induction requires much higher frequencies. Specialized electronics convert current to extremely high frequencies, tens of thousands of times per second. The circuit board monitors power, temperature, and operating status. Sensors detect compatible pots and stop energy transmission immediately if incompatible. A cooling fan is essential because electronic components also generate heat and need cooling. Heat doesn't appear unless there's a compatible pot on top. The real secret lies in the moment when magnetic field meets pot bottom and creates invisible electrical currents. The magnetic field is a real physical phenomenon everywhere around us. But unlike a refrigerator magnet, it constantly changes. This constant change is the key to creating heat without flames. If the magnetic field stayed still, the pot would receive almost no energy. Imagine a perfectly calm lake. Without waves, energy cannot travel. But when waves continuously appear, energy spreads across water. The changing magnetic field works similarly, invisible waves spreading through space. The electrical current in the copper coil changes direction tens of thousands of times each second, creating constantly moving energy. This magnetic field passes through the glass with almost no resistance. For the magnetic field, glass acts like a transparent window. Everything changes when this field encounters a pot made from appropriate material. Inside, metal exists countless electrons that can move freely when exposed to electromagnetic effects. When the magnetic field constantly changes, these electrons start getting pushed along new paths. The magnetic field is forcing electrons inside the pot bottom to move at extremely high speeds. Whenever electrons move through metal, they continuously collide with their surroundings. These collisions convert energy into heat inside your cooking pot. This creates special swirling electrical currents called Foucault currents, the true heart of induction technology. According to the law of electromagnetic induction, the changing magnetic field forces electrons to begin moving in organized ways. These electrons move in complex closed loops, resembling whirlpools. Scientists call them eddy currents or Foucault currents. When moving at high speeds, electrons continuously collide with atoms and other electrons. Each collision converts kinetic energy into thermal energy. Trillions of collisions happen every second, causing pot bottom temperature to rise incredibly fast. This is why water boils in just minutes without any flames appearing. The most special aspect is that heat gets created right inside the metal, rather than being transferred from outside. Your pot becomes the primary heat source. More Foucault currents mean more heat generated. This allows induction cooktops to respond almost instantly when you change power levels. Simply adjusting the magnetic field intensity changes the entire heat creation process inside the pot. But if heat gets created right inside the pot, why does the glass surface below remain relatively cool. Here lies the biggest secret of induction cooktops. For materials to generate heat through magnetic induction, they must allow Foucault currents to flow inside. Metal does this very well because of its free electrons. However, ceramic glass has a completely different structure compared to metal. In this material, electrons cannot move freely like they do in steel or cast iron. When the magnetic field passes through the glass, almost no strong Foucault currents form. Without these eddy currents, the heat-creating collisions never happen. The magnetic field essentially bypasses the glass and concentrates most energy into the pot bottom. You could think of the glass as a transparent window to the magnetic field. This is why most electrical energy converts into heat inside the pot rather than inside the cooktop itself. This mechanism helps induction cooktops achieve much higher efficiency than traditional cooking technologies. However, if you touch the glass right after cooking, you'll often feel quite high temperature. Most heat comes from the hot pot sitting above. When a pot's bottom reaches very high temperatures, heat transfers downward to the glass through direct contact. Therefore, the glass can become hot after extended cooking, even though it's not actively generating its own heat. Not every pot works perfectly on induction cooktops. Some heat water incredibly fast, while others create no heat at all. Interestingly, size or price doesn't determine whether a pot will work properly. The real secret lies in the material used for the pot's bottom. Since induction cooktops create heat through interaction between magnetic fields and metal, not all metals respond identically. Materials like steel or cast iron work exceptionally well because they have strong magnetic properties. When the magnetic field affects these materials, Foucault currents form efficiently and generate heat quickly. This is why many induction-specific pots use steel or similar materials. Meanwhile, pure aluminum conducts electricity beautifully but interacts poorly with magnetic fields. Copper has the same problem. It transfers heat wonderfully, but doesn't work well with standard induction cooktops. Therefore, many traditional aluminum or copper pots won't perform effectively on induction cooktops. Glass and ceramic barely participate in induction at all. To solve this problem, manufacturers developed very clever multi-layer pots. The outside might be aluminum or premium stainless steel, but underneath typically contains a magnetically responsive material layer. There's a simple home test. Just use a small magnet. If a magnet sticks firmly to the pot bottom, that pot will almost certainly work on induction. In any cooking system, efficiency shows what portion of energy actually cooks your food. With gas cooktops, much of the flame's heat never reaches the pot bottom. Instead of going into food, that energy heats air and makes kitchens uncomfortably hot. Traditional electric cooktops face similar problems when they must first heat the heating element. Heat then transfers from the element to the cooktop surface, then continues to your pot. Each intermediate step creates energy losses that users ultimately pay for. Induction cooktops approach this completely differently. They deliver energy exactly where needed from the start. Heat gets created directly inside the pot bottom. This dramatically reduces the energy wasted before participating in the cooking process. This is why water typically boils faster on induction cooktops, even with similar power ratings. Another advantage is the nearly instantaneous response when changing power levels. Heat generation can increase or decrease on demand. This allows more precise temperature control when preparing dishes requiring high stability. High efficiency also means less heat dispersed into the surrounding kitchen environment. Regarding safety, induction cooktops operate at much lower frequencies compared to ionizing radiation types. Under normal use conditions, the magnetic field concentrates mainly around the pot bottom area. Its intensity decreases very rapidly as distance increases. This is why most energy stays near the cooking area rather than spreading throughout the kitchen. Modern manufacturers must follow very strict safety standards before products reach the market. For most ordinary users, induction cooktops represent very safe cooking technology. Fire and fuel leak hazards are actually reduced significantly. Beyond the kitchen, magnetic induction principles find widespread application in modern industry and technology. From metallurgy and precision manufacturing to wireless charging, everything exploits similar phenomena. An invisible physical principle, once confined to laboratories, has become a familiar tool in everyday life. Next time you see water boiling on an induction cooktop, you'll understand that your pot is actually creating its own heat from within. When you think about it, what invention could possibly be more amazing than that?